Hi all, welcome back to my channel. My name is Mohini Yadav, and if you haven't subscribed to my channel, then please click on the subscribe button. Right? You can also click on the bell icon in order to receive the regular updates, and in case you like my video, then please do like, share and comment. Thank you. So in this video, we'll be discussing about the very important questions of Cobb Douglas production function. There are 3 questions, and if you are confident about these 3 questions, then I can guarantee that you can solve any question of this Cobb Douglas production function. And before moving to the questions, first we'll revise about this production function. So this function represents the technological relationship between the factors of production and the output, and this is the basic form of Cobb Douglas production function, where Q is quantity of output, L is labor, K is capital, A is positive constant, and alpha and beta are also constants between values 0 to 1. And strict Cobb Douglas production function says that alpha plus beta is always equals to 1. But this is just the strict Cobb Douglas production function. It doesn't hold true always. So suppose this is our first question where your quantity of output is given and you have been asked to calculate the marginal products of the two inputs when 15 units each of labor and capital are used. So we are asked to calculate the marginal product of both the inputs. So we have written our original output level, then we have calculated the marginal product of labor, which is the partial derivative of output with respect to L by keeping K as constant. So now this is 10 minus 0.1 into 2 L raised to power 2 minus 1. So that is 0.2 L. Then plus this is 0 because this is constant. This is also 0 plus 2K. So this is your MPL equation. Now you can substitute the values L as 15 and K as 15. So when you substitute it, your answer is 37. So how will you interpret it? You will say that if in the current production 15 units of labor and capital are used, then if we introduced one more unit of labor, it will result in the production of additional 37 units of output. Okay, so this is how you can interpret the results of marginal product. Similarly, you can calculate the marginal product of capital, and similarly you have to calculate the partial derivative of output with respect to K by keeping L as constant. So in this case, this is 0, this is also 0, this is 15, this is minus 0.2 into 2, K raised to power 2 minus 1, so that is 0.4K plus 2L. Okay, yes, it is 2L because this is constant. So this is wrong. It should be L here. And when you substitute the values as 15 and 15 units for L and 15 units for K, you will find that this is 39 units. So similarly, as you interpreted about the MPL, it means that if in the current production 15 units of each labor and capital are used, it means one more unit of capital will result in the production of 39 more units of output. Okay, I hope this interpretation is clear. Now we'll move to the next subpart, that if 15 units of labor are used, then what is the upper limit for the use of capital which a rational producer will never exceed? So it means it is given to us that 15 units of labor are used. So what we'll do? We'll substitute L as 15 in our original output function and we'll make our equation in terms of K. Okay, so this is the first step. We have substituted 15 in place of L. So this is our equation that we have solved after this. So this is our equation. This you can practice please side by side by pausing this video so that you are at pace with me. Then after calculating this, you are calculating the marginal product of capital, that is partial derivative of Q with respect to K, and this is now by keeping L as constant. So this is 45 minus 0.4K plus 0. Now you know that a rational producer will incorporate the use of capital in the production function as long as the marginal product of that capital is greater than or equals to 0. If it is less than 0, then he will stop producing it. So you will simply replace your equation in place of this in the place of this MPK. So when you replace it, so your this 0.4K will shift to the right hand side. So this is positive. Now you will simply divide 45 divided by 0.4. So this is the units. So it says that the rational producer will never exceed the use of 112.5 units of capital in its production function in case 15 units of labor are used. So this is the upper limit. So in case the upper limit of labor has to be calculated, then you can do this with respect to labor. Okay, so this is how you can solve this. Now example 2. In example 2, this is your daily output level, and you have to use the concept of total differentials in order to estimate the percentage by which daily output change if capital and labor are both increased by 5%. So this is very simple. This is your output level, and you already know the formula for total differential of the function. In case you don't remember this, please watch my total differential video where I have discussed about this formula and you can understand this. So now you know this formula. This is the partial derivative of q with respect to L. Just replace z with q and xy as L and k. So your equation will be this. Now just find the value of this, that is partial derivative of q with respect to L. So this is under this is 16k 1 by 2 as it is, because these are constant, and L 1 by 3 is 1 by 3 into L raised to power 1 by 3 minus 1. So this is your answer. Then again you can calculate for the MPK by keeping LS constant. So 60 L 1 by 3 as it is, k raised to power 1 by 2 will become 1 by 2 k raised to power 1 by 2 minus 1. So this is your MPK. Now you simply substitute the values in this equation and this becomes your equation 1. Now you know that both labor and capital are increased by 5%. So it means you know this change because this DL represents the change in labor and DK represents the change in capital. So you already know this. So you'll simply substitute DL as 0.05 L because this is 5% increase. If it would have been 3%, so it would be 0.03. If it would have been 7%, then 0.07. So similarly, you can use any percentage of increase by keeping this DL equals to that percentage change. So similarly, DK is equals to 0.05K. Now you will substitute these values in your equation 1 that we have obtained earlier. So when you substitute this, so this will become 20K 1 by 2 as it is, L minus 2 by 3. So this is one more L. So you'll add 1 into it. So 20 into 0.05 will become 1. K 1 by 2 as it is. This will become L 1 by 3. Similarly, when you multiply 30 with 0.05, it will become 1.5. L 1 by 3 as it is. And there is one additional K. So you'll add plus 1 to the power. So it is K minus 1 by 2 plus 1. So this will become 1 by 2. Okay, now you can take K 1 by 2 and L 1 by 3 as common. So when you take this common, this is 1 plus 1.5. So this is 2.5. But your original production function is 60L 1 by 3 and K 1 by 2. So you need 60 here. So you'll multiply this with 60 and divide with this, divide by 60. So 2.5 divided by 60 is 0.0416 and you multiply 60. Now this is your original output level. So this is 0.0416. So it says that if both labor and capital are increased by 5%, your output will increase by 4.16%. So it shows that the production function has decreasing returns to scale. If it would have been 1, it means constant. If it would have been 5, sorry, because they are increased by 5. So if it would have been 5, it means constant. If it is more than 5, it means increasing returns to scale. But in this case, since it is less than 5, so it has decreasing returns to scale. I hope this is clear. Now this is example 3. This is your production function. Now first step is you have to find the nature of the returns to scale. So in order to find it, you will check about the homogeneity condition in order to find the power of lambda. Please watch the videos of homogeneous function if it is not clear. If it is clear, then you can simply move. So in this case, just add lambda along with L and along with K, and replace L with lambda L and K with lambda K. So when you replace it, then you can take lambda as common. So the powers will be added. So 1 divided by 5 plus 1 by 2 is 7 by 10. And this is your original function. So in this case, the power of lambda is 0.7, which is less than 1. So it shows decreasing returns to scale. If it would have been 1, it means constant. Greater than 1, it means increasing returns to scale. So in this case, it is showing as decreasing returns to scale. The next question is, can elasticity of substitution be 1 even when the returns to scale are not equal to 1? So for that, we'll find the elasticity of substitution. So before that, we'll find the marginal product of labor, because this will be used in the formula. So marginal product of labor, you already know that the partial derivative of Q with respect to L by keeping K as constant. So in this case, K 1 by 2 as it is into L 1 by 5 will be 1 by 5 into L 1 by 5 minus 1. So this is your MPL. Similarly, you can calculate the MPK by keeping the L as constant. So this is your value. Now you know that in the formula of elasticity of substitution, you also require the marginal rate of technical substitution, that is R. And the formula for R is MPL divided by MPK. So when you simply divide this, so 0.2 divided by 0.5 is 0.4. L raised to power minus 4 by 5 minus 1 by 5, because this is in the denominator. So this will be subtracted here. Similarly, K 1 by 2 minus plus 1 by 2, because minus 1 by 2 is now in the denominator. So it will be added. So when you will solve this, the value will become 0.4 K divided by L, because the power of L is minus 1. That is why it is positive 1 in the denominator. Now, the formula for elasticity of substitution is the derivative of K by L divided by K by L, derivative of R with respect to R. Okay. So this is the derivative, not the partial derivative. Okay. We are not going to keep anything constant now. So this is as it is. Now this is your R. So when you find the derivative of this R, so this will be 0.4 is constant. So this is as it is. Derivative of K by L, because this is not constant. So this we are just adding the D sign here, and you can divide with R. So the full R is 0.4 K by L as it is. So you just have added the value of R. Now this dk by L and dk by L will get cancelled, K by L and K by L will get cancelled, 0.4 and 0.4 will get cancelled. So in this case, the value is 1. So it means it shows that even when the returns to scale are not constant, means not 1, our elasticity of substitution can be 1. So this is proved. Okay. Now the third important part is that you have to verify the Euler's theorem, and the Euler's theorem is this. If you don't remember this, and if you're finding any difficulty in remembering this, then please watch the video which I have created specifically for Euler's theorem. Okay, so this is the theorem, and that you have to learn. In this case, we have already calculated this MPL, we have already calculated MPK. We'll simply substitute the values here, and when you substitute it, 0.2 will be as it is. There are 2 L, so you'll add plus 1 in the power. So this is minus 4 by 5 plus 1, K 1 by 2 as it is. Similarly, 0.5 as it is, L 1 by 5 as it is, and there is one more K, so you'll add plus 1 in the power of K. When you solve this, so minus 4 by 5 plus 1 is 1 by 5, K 1 by 2 as it is. Similarly, L as it is, K power is 1 by 2. So you can take L 1 by 5, K 1 by 2 as common. So this is 0.2 into 0.5. So this is 0.7 into, this is your original function output. So from Euler's theorem also you can say that 0.7, since this is the degree and it is lesser than 1, so it means the production function has decreasing returns to scale, and your Euler's theorem is also satisfied. In case of any question, please reach out to me. Thank you for watching.